Soumya, you tell me when is time to begin according to you.
Yes. Yeah. Maybe 30 seconds more.
Okay.
Yes, sir. We can start.
Okay. So let me welcome you all to this session of Math Clinic. Today we have with us Professor Habib. He is professor at the Shiv Nadar Institution of Eminence in Gautam Buddha Nagar, UP. This is attached to, I think, Shiv Nadar University, this institute, or is it independent? I don't know.
This is actually Shiv Nadar University's new name.
Oh, it's a new name. Okay, okay, fine. I didn't know that. So thanks for correction. Before joining there, he has been to Mathematical Sciences Foundation, Delhi, and also teaching at St. Stephen's College. He is a product of IIT Kanpur, MS in Mathematics, and PhD from California, Berkeley. His interest in mathematics is in representation theory and, of course, mathematical finance. He has authored 3 books. One is called Undergraduate Mathematics Foundations. Another one, A Bridge to Mathematics. And third is Calculus for Finance. So let me not take too long a time, but his passion is math education and in particular math education. He has been doing a lot for various schools, colleges, NCERT, and so on. His motivation in mathematics education is to bring down number of students who tell him that I love, bring down students who tell him that I love mathematics in school, but I hate it in college. Okay. In fact, there is a slight, you are in a pleasant situation number because whenever I talk to students, whether school or college, they say I hate mathematics. School, college, but school also. But anyway, with that, let me just add that his hobbies are nature photography and especially birds and butterflies. So let us welcome Professor Habib for today's presentation on mathematics in finance.
Okay.
Please.
Okay, so thank you, Professor Anna, for the invitation, the introduction. As long as I've known him, Professor Anna has always been one to make you think and to ask you a question where you tend to think superficially and give the wrong answer. so let's see. Let's see how today goes, and let's see if we can provoke him into asking some of those questions. Okay, so now, I got into this business of thinking about finance quite by chance. I had all my training as a pure mathematician. But when I started teaching at St. Stephen's College, there were already some special kind of programs happening there because the faculty had realized that the way that the curriculum was set up, even though they were getting sort of, the top students in terms of marks and performance in schools so far, but still if 60 people were admitted to the undergraduate program, then maybe 5 or 6 went away happy and the others were not. So one of the things they tried to do was to, one reason for this was that mathematics as a discipline seemed to be divorced from everything else happening in their lives. And if you just completely enjoyed mathematics for its own sake, then the curriculum to involve students in different kinds of projects. And out of those also grew the idea of short sort of courses in applications of mathematics or leading courses, or again, or more serious ones. And eventually a rather a year-long program in finance was formulated where students would do voluntarily, the ones who were interested in the evenings. So when I joined St. Stephen's, all this was already happening there, and pretty soon I got involved in it. And that was the first time I had to think about finance. I went into it expecting that it would be a bit of a core, but very quickly, I found that it was quite fun. And it started reminding me a bit of how maths had been fun in physics classes, and one was getting the same sense when looking at how it is applied in finance. And the ideas were quite non-trivial. There were pictures to be drawn, everything that you would want to do as a mathematician, you could have. And also it had a very strong effect on the students, being able to participate in such a course. Things like linear algebra, probability, and statistics took on a new life for them. And I think one success story is that several of them were lured back into pure mathematics through this diversion of, getting them excited again through the use of finance. Okay, so it's not just that things like this, take you into applications. They generally excite you about mathematics, and the outcome could be that you go into a career in applications, but it also could bring you into pure mathematics as well. So I want to share a little bit of that today, some basic concepts, and you will see that, what I will do today will not get perhaps too advanced, but still you will see sort of nice applications of calculus and so on, and basic probability perhaps in financial planning. Okay. So I will share my screen now and start writing. Okay, so I hope this is visible. Okay.
Yeah.
Yeah. So let's see, we are talking about this word finance, and it could mean different things. One thing it often means to people is essentially accounting, right? You might think that finance is just about balancing your books, figuring out what you have in your bank account, how much you owe or are owed. And of course, that is a part of it. But the part that is really interesting for a mathematician is the part about investment. Okay, or investment science, if you want to give it a more attractive sort of name. So what's the goal here? The goal is that basically whatever you own, you want to choose the things that you own so that their value will grow with time. Okay. All right. So finance is very specifically, when we say mathematical or computational finance, we are talking about this last question, that how do you invest your money so to make it grow the most, okay, over time. But that is a kind of vague question, and we have to make it more specific, and we'll see there are different aspects to it, and there are choices to be made, and that influences the mathematics that you will do. Well, let's suppose, that you suddenly had, a lot of money, and you wanted to do something with it. Of course, you could just spend a chunk of it and make your life nice right away. But suppose even after all that, you still had a lot left, and then you would want to plan for your future with it, right? So what could you do? There are many things you could do. You could take your money, and you could be worried that someone will steal it, so you might bury or hide it somewhere. And historically people have done this a lot of times. Okay. You might go for a safer version of this. You might put it in a deposit box in a bank, in a locker in a bank. But you might have more ambition than that. Rather than just preserving it, you might want it to grow. And so for now, of course, there are still many options. You could put it in a savings account. You could put it in a fixed deposit. You could buy bonds. You could buy shares. Okay. Or you could invest in many other things. People like to invest in gold. They like to invest in real estate, etc. Right. So there's no end to the list of things that you could try. You could invest in famous paintings or whatever. Okay. Or actually, there are many options, right? And I think one thing we can sense is that these will all have different properties in some way. And the potentiality for how much your money will grow will be different. And it will not only be about growth, right? None of these is entirely safe. Things could also go wrong. So that is one key issue, that things don't have to go well. They could go badly. You bury it, someone may find it. You put it in a bank, the bank can get robbed. You put it in a savings account, that's better, but things still happen. People still find ways of withdrawing it, or maybe the bank collapses. So all sorts of things can happen no matter what you do, right? Okay. So the story with investments, we will come back to these types in a bit. Okay. But there are kind of two, let me say, issues, right? There's the issue of what you want, and there's the issue of what you fear. What you want, of course, is that your money grows as much as possible. So you want to maximize the growth. What you fear is that you can't be really sure of what will happen, right? So what we fear is uncertainty. And in the world of finance, this uncertainty is called risk. Okay. So risk is basically that you don't exactly know what will happen once you have put your money into some particular investment. Okay. Okay. So these are sort of the two things that sort of play off against each other: growth, expected growth, planned growth, but the risk that things may go wrong, right? So growth or profit versus risk, this is the playoff that one has to analyze and understand, and then utilize that knowledge in finance. Okay. Let's go back to these different kinds of investments. Okay. In the first two, there really is, of course, no question of growth. You are just hoping for as much safety as you can. And you're just purely trying to minimize risk as much as you can, but you're not going for profit at all. In a savings account or a fixed deposit, you're going for a small amount of profit. You are exposing yourself more to the fact that somebody else now has possession of your money, and you are dependent on what they do with it. Okay. Now, what is a bond? So bonds are what we will spend most of our time today, because out of all these, we can't really look at everything. So we will just pick one and look at that, right? But a bond is in some way like a fancy fixed deposit, right? You give your money to someone, and they periodically give you some amount back, and maybe eventually whatever is with them, they give it all back to you. So you give someone some money and you get periodic payments in the future out of that, right? So that is what a bond is supposed to get you. The way in which bonds are different from the previous four is that it is possible not just to buy a bond, but it is also possible to sell it. So these are things that you can trade. And so there's a market in it, and that opens up various possibilities that can be exploited by investment people. Okay, these are kind of the safe investments of different types. Now, beyond that, if you're more ambitious, you might buy shares or you might invest in gold or real estate, etc. Here, you would be trying to really get more profit, but you would also simultaneously definitely be exposing yourself to more risk. Okay. Maybe we can, now, once we want to involve maths in all this, the whole thing is that, the point is not to just talk about it in a sort of vague way that I've done so far, but to introduce numbers so that you can count and measure, and then you really have some mathematics going. Okay. So let's introduce some basic terminology here. Take any object that you are interested in investing in, or perhaps you already have invested in it. It has a certain value now. So let's give that a name. So let V naught be the value, whatever object whose value we are worrying about, let's call it an asset. So value of this asset now, and the current time, let's agree to call it time 0, right? So let's call that V naught. And you could be interested in what would be its value after some time. Let's call that VT, the value of this asset at some later time. Okay. What are we interested in? How much the value V naught will grow, right, into VT. So we are interested in the difference, VT minus V naught. This is called the return over this time period. Okay. Over this time interval from 0 to capital T. Obviously, we want this return to be large, right, and positive. Now, if I say, if I tell you here's an asset and I'm expecting a return of 1,000 rupees from it over a year, and here's another asset and I'm expecting a return of 10,000 rupees from that over a year, one might think that the second asset is a better one than the first one because it's offering a gain of 10,000 versus 1,000. But that, of course, is not the full story, right? What also matters is how much you put in to get that profit. So how much did you put in to get that profit of 1,000? How much did you put in to get that profit of 10,000? If you got that profit of 10,000 by putting in 1,000, but if you to get 10,000, you needed to put in 100,000, then the 10,000 profit is not so attractive, right? You had to put in much more to get it. So it's not just how much you get, it's also how much you get compared to how much you put in. So, right? So that's actually the key number. And that's called the rate of return. Okay. So you take the return, but then divide by the initial value that you had, right? So how much did you gain per unit that you invested? Okay. So this is the key number that we look at. Okay. For an investment, this is the number, the rate of return that we want to be high. And we will usually denote this by the letter small r. Okay. Just a second. All right. Now, as already mentioned, this R is generally will not be known actually, right? You will have some analysis, you'll have some hopes of what this R should be, of what VT should be. But generally, you will not know VT ahead of time. So if you invest your money in something, what will come from that in a year will not be known at time 0. Of course, it will become known after the year has passed, but it will not be known initially when you are making the investment. Okay. So what you have to imagine is that this R, maybe it has various possible values. Right now, let's just pretend only finitely many, but all this can be extended. What we'll do can be extended to when there are infinitely many possible values as well. And each of these values has some probability. Okay. All right. So different things could happen, and each thing that could happen has a certain probability. How do you get some overall sense of how good is your situation? Well, what we will measure it by is try to ask on average what will happen. So, think of what probability is supposed to represent, right? So let's take the relative frequency interpretation of probability. So if you say something as probability 0.4, there's some random experiment and some particular event has probability 0.4, you are saying that if you run the experiment many, many times, then around 0.4 times or 40% of the time, you will expect to see that particular event, right? So that is what probability is supposed to represent. Okay, so each probability represents how often these different rates of return might occur if the experiment could be repeated. And so what would we expect to see on average? This is called the expected value of R. Right? So if you know probability and random variables, then this would be familiar to you. But otherwise, think of it from a common sense perspective. We will denote this by R bar, or sometimes by capital E for expectation, okay, of R. And what we say is, okay, for example, suppose all these values were equally likely, right? Then what would be natural to take for their average? For what would happen on average, their actual average. Just add them up and divide by their total number. So if each had probability 1 by n, you would simply sum up 1 by n times each Ri. And if they have different probabilities, then replace those 1 by n's by the corresponding actual probabilities, and that is your expectation. Okay. So this is called the expectation. Okay. This kind of weighted average of the various possible rates of return. Okay. So this represents what you expect to happen if things go in a normal sort of situation. But then you're also worried about what are all the possible things could happen, not just what will happen on average. And what is risk? I said it was uncertainty. What is uncertainty? How much deviation can you have from the plan, right? So you have some plan that you want to be in a certain location. What are all the other locations? How far are they? How spread are they from the central location where you actually want to be? Okay. So what measures that in probability is the concept of variance and its square root standard deviation. So you also look at the variance of this rate of return. Okay. That one may denote by sigma square, or I might sometimes denote it by V, capital V. What we do is we take the mean value, we ask how far the particular value could be from it. We don't want to differentiate between positive gaps and negative gaps, so we square. And again, take the average, but using the probabilities as the weight. Okay, so this is called the variance. Okay. All right, so this expected value in finance is used to represent expected profit from whatever you are doing. And this variance represents risk. Okay. All right, so there are different ways to measure risk depending on what you are concerned about. But this is the most common way to measure risk by looking at the variance of the rate of return. Now, let me just share sort of, what you could call experimental data about rate of return and variance. Okay, suppose you took many assets and actually measured over some time span what happens to their value and how much their value fluctuates over time. And you plotted this combination, how much it grows on average over a certain time, but also how much fluctuation there is over a certain time as represented by R bar and sigma square. Okay. So suppose that you plotted, say, sigma, the root of the variance, the standard deviation on one axis, and R bar on the other axis. Okay. And you just measured and went, and the people have done this repeatedly, and you always come up against the same sort of rough pattern, which is that when you plot sigma and R bar for some asset, of course, it could happen anywhere. Okay. It could also be negative. Okay. Because you might lose money. But typically you see some spread like this. Okay. All right. So this is sort of the typical situation. Okay. So what's happening in this typical situation is that you see that there is a certain region which doesn't have anything, right? There's nothing here. The green parts are on sort of one side of your quadrant. So what does it mean that there's nothing here? It means that if you don't take risk, you do not make your expected profit, it does not have a chance of being large. Right? If you want, if your expected profit is low and you want to plan for that, there are many ways to do that. And there could be low risk ways, which are over here for low expected profit. There could be high risk ways over here. But if you want high expected profit, there is no help for it. You will just have to go for higher risk, right? You'll have to be somewhere here. So the general principle that I said before, that to go for more profit, you will need to take more risk, and we sort of formalized a bit in terms of expected value and variance. Okay, what we see here is that to obtain higher R bar, we must live with higher risk, with higher sigma. Yeah. Okay. Anyway, so in all this that I'm talking about, of course, this is really the fun part that people, investment scientists earn their big salaries for. I mean, how to figure out this playoff and how to manipulate it. Today, we will not go there. Today, we will look at bonds, and bonds live somewhere over here, okay, with low risk and low rate of return as well. But then that's important, right? Now, you can't always be taking risks. And so the buying and selling of bonds is a very large part of modern financial activity. Okay. Okay, now there is one concept we need before we can really look at bonds, and this is called the time value of money. Okay. So let me ask you a question here. That suppose you had to choose between two kinds of investments, or somebody just makes you two offers, doesn't even ask for anything from you. It's somebody that you trust completely, and what they offer you is rupees 100 right away, or else they say you can have rupees 110, but after 1 year. Okay. And the question is, which is the better offer, right? Which one should you go for? Of course, one thing you could worry about is, money that you get now is money that you get now, but what if he's not around after a year? But let's assume that this is someone completely trustworthy, or maybe it's a completely trustworthy institution. You have no real fear that they will not be around after a year, or that they will not fulfill their promise. Okay. Assuming that those fears are not there, which is the better offer? Would you rather have rupees 100 immediately, or would you prefer to wait for a year and then get the 110 rupees? Okay. So these are two amounts of money existing at different points of time. Okay. And the issue is, how do you compare them? How do you compare some amount of money which is existing now with some amount which will exist in the future, right? Okay. So, well, one way to think about this is that if you had the money now, 100, what could you do with it? And if you could use it to get more than 110 a year from now, then you would like to get that 100 now, right? But if you did not have a way of investing that 100 to get more than 110 after a year, then it's probably better to wait and get the 110 which the other person is offering. Okay. So that is the way to think about these problems. Okay. You ask, what could I do with this money if I had it right now? And how much could I make it grow? Could I make it better than 110 after a year? If the answer is yes, go for the 100. If the answer is no, go for the 110. Okay. But of course, then there are many things you could try, and there's no guarantee what any of them will do. So the only sensible way to really tackle this question is to say, is there any way that you can, investment that you can treat as certain, that will certainly get you 110 after a year, right? Okay, now in the world of finance, the only thing that is really taken as certain is, for practical reasons, because even what I'm going to say now is actually not completely certain, but you have to settle for something. And what people generally settle for is, okay, what can you get, say, from a fixed deposit in a government bank? What could you get from State Bank of India? Okay, so that it is something that you're pretty sure you will get, unless, the whole country and the bank has collapsed, in which case it would hardly matter. All right. So you can ask, what kind of interest rate can I get, right? What interest rate is available for a 1 year deposit in a safe bank? Okay. Well, suppose what's available is 5%. Then, of course, your 100 will only grow to 105. And then it's better to wait and get the 110 later. And even if, you are in dire need and you need some money right now, the better thing would be to borrow something right now, as long as you could get it at an interest rate which is less than 10, right? And then when you get the 110, you could pay back the loan, and in between you would have had your money as well. Okay. So basically, we use interest rates to compare amounts of money that exist at different points of time. All right, so suppose an interest rate of R is available over, some time t, starting from time 0. Okay. and you had an amount A at time equal to 0, right? Then how much would it grow? So it would grow by this fraction R, right? So you had your A and then you would get R times A, right? And so at the end, you would have 1 plus R times A. So this amount, which this A will become in the future, is called its future value at that time. Okay. And conversely, A is called the present value of that future amount. Okay, let's call this AT. Okay. So if to a perfectly safe investment, your A will become AT, then that AT is called the future value of A, and A is called the present value of AT. And what this simple observation allows you to do is that now you might have some complicated investments, deposits of different durations, something for 6 months, something for 1 year, right? And many others. And you want to get an overall sense of what's going on, right? How much do you have? What you can do is look at all the amounts that will exist in the future and simply find the present value of each of them. And then you can sum that up and say, okay, whatever I had for the future, if I bring it to the present, what is it worth today? You compute this total present value. Okay, let's do this through a diagram. So let's say this is a time axis. Okay. And there are different times, and you have made some investments. And let's say at different times, these investments are going to get you different amounts of money in the future. Okay. So let's say this is time equal to 0. Let's keep things simple. I mean, this could be very weird times, but let's just assume this is, say, after a year, 2 years, 3 years, 4 years, 5 years. This is what you're going to get. These are different amounts. Let's say you're going to get these amounts C1, C2, C3, C4, C5. What kind of value does this represent today? Okay. So what you do is you ask how much money today would grow into C1, right? So you ask what is the present value of C1? And if the 1 year interest rate was R, then that would be C1 divided by 1 plus R, right? Because look, what you have in the future is 1 plus R times the present. So the present value is what you'll have in the future divided by 1 plus R. So that's why divide by 1 plus R. This is what this C1 represents today. What does C2 represent today? You have to bring it to the future, but now this is happening over 2 time periods. So the 1 plus R would be applied twice, and therefore you would have a square. And similarly with C3, C4, and C5. Okay. This is called NPV, or net present value. Okay. So if you have a bunch of investments, you can figure out where you really are today. Or if you had a choice between two such things, how would you compare? Different amounts happening at different times, it can get confusing. So the simple solution is for both, find the net present value and then compare, right? See which one is worth more today, go for that. Okay. All right, well, we need to get to some more interesting maths than this, but we are setting things up, right? We have been able to sort of quantify the key issues. Now let's come to bonds themselves. Okay. So what is a bond? Well, the English word bond means promise. So a bond is a promise. It's a promise of future payments. Now, the promise could be very complicated, but we will work with today the simplest kind of bonds, what are called plain vanilla bonds. Right? So vanilla ice cream, the one which has no sort of special flavors, so no complications. Okay. So what is such a bond? Again, let me represent it by a drawing. Okay. Let's have the time axis. Okay. We'll have some arrows to represent, what future payments are being promised to us. So what happens in such a bond is that certain things are promised in the future at regular intervals. Okay. Like this. Plus at the very end, an additional payment of something. Okay. So regular equal payments all along, plus together with the last of those, an extra payment of something. Okay. Now, these are called coupons. In the old days, you would actually get a coupon for each payment, and at the right time, you would hand in that coupon to get the payment. Now, of course, the money just goes straight to your bank account electronically. Okay. So there are these regular coupons, and then this extra one is called the face value of the bond. Okay, the extra one that is offered at the end. Okay. Again, let's assume this is happening annually. So at the end of 1 year, you're promised this coupon payment and 3 and 4 up till some nth year. But in your final, at the end of the final nth year, you get the final coupon plus this face, right? Okay. Now, all these coupons have the same value. Let's call it capital C. And this face value, let's call it capital F. And it need not have anything to do with the C. Sometimes the test may be 0. Okay. So in fact, there are some special cases. Okay. One special case is when there are no intermediate coupon payments, there is only the face value payment at the end. Okay. So these are called 0 coupon bonds. So that's one special case. Okay. Another special case could be when your F is 0. Okay. Another special case is okay, so you just get these, and if you're getting them annually, then this is called an annuity. So just a regular annual income with no special payment at the end. There is one interesting thing which I don't think these exist anymore, but they used to exist in the past. Okay. Where the promise is that you will get a certain fixed amount forever. Okay. So this is called a perpetuity. And these used to be quite common in Europe in the 18th and 19th centuries. But there was huge inflation after World War I, which made them all useless. And as far as I know, they have not been resurrected. Okay. Now, anyway, so let's take a general bond with these fixed payments of C and the face value. Then what is it worth today? You will compute the net present value. Okay. So for each coupon payment, you will bring it to the present by doing this. Plus, you will do it for the final face value as well. You will bring that by dividing by 1 plus r raised to the power n. So that's okay. So what is this NPV? This is the amount that you would be willing to pay for the bond, right? This is the value of the bond today. So if somebody were to offer you this stream of payments and say, give me some money now in return for these future payments, this NPV is what you would give to them. Okay. Now the question is, in all this, what is R? Okay. I started by saying it would be what you would earn as interest by putting in a savings bank or something like that. Okay. But in reality, when it comes to actual bonds, could be a little bit different. What happens is that somebody is issuing that bond, and in general, there could be some doubt about their capability to really keep the promise. Okay. And there could be other factors. So typically what happens is that due to various factors, state of the economy, general sort of emotion in the market, or specifics about who is issuing the bond, this R may not be exactly what you could get by putting money in a savings account, but just some number which represents how much profit people want from this bond. Okay. So somehow the market decides, people decide based on their knowledge of what's happening, what kind of profit they want from that bond. That becomes the R that they use in these calculations. And then based on that, they use this formula to compute the present value and decide how much they will pay for it. So this is called the expected yield. Okay. So it's an external number. Not coming from the bond, but by people's perception of the bond. And so they decide, and according to that, they figure out how much they should pay. Okay. Now, it becomes useful to ask, how does this price depend on this expected yield, right? Because now this expected yield has become a variable, and it could change with time. And so now we have to worry about these issues. Okay. Now we get to something interesting. Well, okay, let me again draw here a graph. Okay. Let's plot the expected yield over here. And whatever price you are going to get out of it, we'll plot here. For example, what happens if people don't want any profit? Right? If R is equal to 0, then you simply have the N coupon payments added up with this F, and the net present value will be here. Okay. Right. So you certainly pass through this point. Another interesting special case that one can just figure out by common sense is what kind of expected yield corresponds to an NPV which is equal to F, right? When would you pay F in order to get all these C and then that F? Well, just visualize this. This is as if you basically loaned your F, and then those C became your interest payments. And at the end, you got the F back, right? And therefore, this corresponds to an interest rate of C upon F, because for a loan of F, you are making these regular interest payments of C. So another thing that one can figure out by common sense is that if the expected yield is C upon F, that corresponds to a value of F. So that's another thing. Okay. And the overall shape, of course, as you increase this R, all these values, each term will decrease, and therefore the NPV will decrease. Okay. And so this, it has to go through this point. But anyway, this is roughly how things will look. It will smoothly go down like this. So this is called the price yield curve. Okay. Okay. So now one can ask different questions. One can ask, what would happen if the design of the bond were different? How would this curve change? Would it be good for the buyer or bad for the buyer? That's one kind of question that one can ask and one can answer with the help of what we have already done. Okay, so for example, suppose I took this bond, that we are seeing here, and I increased the number of coupon payments, right? Now, is that good? Should you pay more for such a bond, right? So first, let's say it had 10 coupon payments and this face value. And now, instead of that, you are being offered 20 coupon payments and then the final face value. Is that a bond for which you should pay more because you seem to be getting more payments out of it? So it turns out it's not so simple, okay? It depends on what is the expected yield where you are located relative to that. Because you see, suppose you were to increase n. And now let's look at how this curve would change. This point is not affected by n, right? It has nothing to do with n. It depends purely on f and c. So however many coupon payments you had, you would plot here. But if you increase your coupon payments, this point moves up, right? And it will now be somewhere here. And therefore the curve would now go like this, and then it would continue, right? So it would fall more steeply. Which means that if your R was over here and you increase the number of coupon payments, then that's good for the person. I mean, then the person who is buying is being actually offered more in terms of present value, right? It has increased and they should pay more. But if the expected or required yield was over here, then in fact the net present value goes down. I mean, the basic idea is the face value, which is generally the main thing, got pushed far away. And the further you are in the future, the less you are worth now. So even though there were more payments, they actually end up being worth less to them. Okay. And so over here, it would actually go down and you should pay less for the bond. So depending on what is the expected required yield for the bond, you would decide and the behavior would be different. Okay. So here is where some mathematics and some ability to plot curves and show how graphs change is already paying off. And we are understanding better how to look at bonds. Right. But the other thing is, what if R changes? Okay. Right. So the typical question here is like this, that you bought a bond, you paid some money for it. It will last, let's say, for 5 years, and you will get these regular payments. But it may happen that after 2 years, you actually need to sell it, right? Because you have a need of money after 2 years. And so then you can't just hang on to the future payments. You need to actually sell this bond and make some money out of it then. But after 2 years, the rates of interest would have changed, market would have changed. So this R that is in effect then probably would not be the R that is in effect now. So the other question that worries people is, how vulnerable is the value of this bond to changes in the required yield R? Okay. Well, now maybe you can guess this is where calculus would come in, because these are exactly the kinds of questions that calculus asks. So we have the value of the bond or the price of the bond. Let's express it as a function of R, right? It looks like this. So I'll just do this one little calculation to show you how calculus is used here. And I expect then it would be time to stop, take questions, and maybe some questions will give me a chance to say more about this. Okay. All right. So what do? You simply asking how vulnerable is the price is to ask, what is its rate of change with respect to R. So you want dP by dR. So you simply differentiate each thing. Okay. So what will happen? You will get C 1 plus R. So this will become I plus 1. You will get an I. You will also get a minus sign. Here you'll also get a minus sign here. So let me just right away put that minus sign on the other side. Okay. And then, okay. Now why I'm writing this summation. And then you will do the same thing here. You will get F and N and 1 plus R, N plus 1. Okay. Okay, but as we happened with return, it's not just, how much the price changes, but how much it changes relative to what it was. So the quantity one is really interested in is this divided by P, right? So this will reflect how much it will change compared to its starting one. Anyway, so that is all this divided by this. So let's see, maybe technology may be useful here. What we are interested in is this divided by this. Okay. Now, what I just want to point out is that this expression, though it looks horrible, actually has a very special form. Okay. First, if you look at the numerator and the denominator, there's an extra 1 plus R in the numerator. So let's take it out. And let's look at the rest. Okay. If you look at the rest, you see that this is like a weighted average. Like this C upon 1 plus R to the I, that is the weight of I, right? And the same weight is occurring here. And then F1 upon 1 plus R to the N is the weight here, which is also occurring here. It's as if you had, well, it actually has this form, alpha I times, each C, the ith C, plus some beta F, where all these alpha I's and the beta are adding up to 1. Okay. So this is a weighted average. So what's happening is this rate of change has a very interesting form. The vulnerability to interest rates has an interesting form. It's actually, you are looking at all the payments. Okay. Sorry, not C and F. I got carried away here. C is part of the weight. The interesting things are the I, the payment time I, and the payment time N. Okay. So it's actually, the times at which you are being paid, okay, and how far off they are. That is deciding how vulnerable you are. But then how important is each time? That is decided by how big a payment is there. Those are the weights that we have here. Okay. All right. So this gives us a particular way of looking at how bond prices fluctuate with time. This particular quantity that I have defined here, this is called duration. Okay. And it reflects the vulnerability of the bonds. With this duration calculation, what you can do is you can create entire portfolios of bonds. And by studying the duration of the combination, right, you can look at the durations of the individuals. And then you can buy the bonds in the right amounts so that the total duration is the one that you wanted. So you can calibrate your portfolio of bonds to have the amount of vulnerability to changes in R that you can live with. Okay. And very interestingly, you can do things like the following. So there's a process called immunization. You can set up your portfolio so that the vulnerabilities that you have between different bonds cancel each other. And so up to small fluctuations of R, the net value of your portfolio will not change. And again, this duration is what you use to do that, because the duration is giving you the vulnerability to changes in R. And having made these calculations, you can then combine these and come up with a net duration for your entire portfolio and have it, sort of planned for whatever time you want. So for instance, if you want to invest in many bonds, but at a particular point in the future, you want to know, how much you will have, set up the duration so that it matches with that time, and you will find that you have a stable portfolio, one that is less vulnerable to interest rate fluctuations. Okay, so I think let me stop here. I have given you some glimpse of how calculus enters the scene. If I had talked faster, I could have given you more, but this is about the speed at which I speak. Okay, so let me stop here and I can take questions from the audience.
Thank you, Amber, for taking us through the nuances of financial mathematics. So let me open the floor to any questions or suggestions by anybody. Hello. Am I audible? I hope.
Yeah, yeah.
Yeah.
Actually, the voice is slightly
okay.
Not getting it clearly
Somebody
right.
has a question, please unmute and ask. Yeah, I think my internet has gone a bit down probably. Okay. Soumya, can you take over the question and answer session, because my internet seems to be slightly down.
Yeah. So anyone have any questions? Yeah. Srinivas sir, you have some questions?
Yeah, I was wondering, so suppose you now look for, let's say, mutual funds or stocks. What are the changes that you need to make here? Because R is not constant there, right?
No, I mean, then, okay, so that is where you have to work much harder. But there are two things you can do. I mean, one thing you can do is to actually try and model the fluctuations in the stock prices. The other thing is to not go into that detail, but do it. For example, you could simply look at past data, and you could see how you could, for instance, look at weekly data or daily data and see, say, at 1 day time periods, how much it has fluctuated over the past year or 2 years, whatever. Right? And this sort of becomes your data from which you would then estimate your R bar and your sigma for that stock. But working with one stock does not lead you to anything very interesting. So the issue is now, suppose I was working with multiple stocks, right? And how should I combine and get a nice portfolio out of those? Then you need to look not just at their individual rates of return and standard deviations, you need to look at the covariances. So you need to see how stocks vary relative to each other. And then you compute, again, from the same data, you can compute the covariances, right? And then you can compute that if I took shares in certain proportions, then for this overall portfolio, what would be my R bar and my sigma? And you would try to vary the amounts you are investing in different shares so that your R bar is at a level that you like, how much you might get. and your sigma is also not too high a level of risk that you can handle. Now the math really comes in then in trying to optimize. So then what you want to ask is, suppose I could live with a certain level of risk. At that level of risk, what is the maximum R bar I can go for? Okay. Or, if I do want a certain R bar level, what is the least, which portfolio has the least associated risk and gets me to that R bar? None of this is a guarantee that things will work out, but this is what you can do. Okay. And this also is nice. I mean, in terms of, what kind of math you need to do this, you need to know Lagrange multipliers because these are constrained optimization problems. So these are actually nice instances. I mean, if you teach Lagrange multiplier, this is something you can do immediately with just a few minutes of explanation of what is involved here. Okay. There's a nice backstory to this portion of finance, which is that the famous name associated here is Harry Markowitz from, I think, finished his PhD in 1952. So he was working with his supervisor in optimization, not quite getting hold of a good problem to solve. And one day when he had come to meet his supervisor, there was a stockbroker also waiting to meet his supervisor. And the stockbroker, they got to chatting while waiting to go in. So the stockbroker said, look, the old books all say that find the thing with the highest R bar and invest in that. But we know that's nonsense because nobody ever puts all their money into one thing. You always put it in diverse things, but we don't know how to analyze that. So Markowitz got to thinking, he figured out he should look not just at rate of return, he should look at standard deviation. He didn't know how to look at combinations. He went to the library and started going through statistics books. And what he says is he remembers, the exact aisle where he found the book, the shelf in which he found the book, and the exact page where you had, the standard formula, okay, what is the variance of a sum of random variables and involving covariances? He saw that formula and he said, aha, okay, I can do this. And so he took it back, he applied that formula, applied his Lagrange multipliers. He had to do a lot more because in the real world, constraints can be mixed and Lagrange multipliers by itself isn't enough to do the trickier problems. He had to work out some basics of quadratic programming to do that. But that's how it happened. It was a very big introductory level book on statistics which led him to this. And eventually he got the Nobel Prize for the work that he did. Except his thesis committee didn't know what to do with this thesis. The economists said this is not economics, and the maths people said there's no new maths in this. Then they sent him out of the room and they argued for an hour. And finally they said, we still don't know what it is, but you are getting your PhD.
Very, very good talk, Amber.
Okay.
So this is one more topic that I've got now, where I can lecture on this after learning. Because, in many places, we need to explain to students what are the applications of mathematics. Right? So I keep doing cryptography as part of that.
Yeah.
Now it is one more topic added.
Srinivas?
Yes.
I think I already asked Soumya that you are in the queue for September talk.
I see. Okay.
On your favorite topic, cryptography.
Okay, fine. Yeah, sure.
I'll get back to you. But
sure.
In the meantime, anybody else has a question to ask, please also fill the feedback form so that we can track what improvements we need to do. Amber, I just wanted to ask something. In the beginning, you said if somebody has 100 rupees and 5% of interest, then probably after 1 year, you can make 105, right?
Yeah.
Supposing, as you also said, probably there is a possibility of a loan at a lower rate. Right? You take a loan and then invest in that, so you don't lose the money, but you get. So is that something like making money without investing anything?
Well, I mean, but this was dependent on somebody having promised you 110.
Yeah, that's right. But it's
okay. So there was,
so,
yeah. But
so
in reality, what it would be is that that 110 would be an exchange of something now, and basically, so I mean that was just to start thinking.
No, I understand. I'm just joking.
But in reality, that promise of 110 would be an exchange for something that you would give now. So the question would be, if I want 110 a year from now, how much is fair to pay this person today? And for that, you would adjust according to the interest rate, compute the present value, and say that this is what I'm willing to pay today for that 110.
Before I ask people to ask other questions or suggestions or comments, please fill up the feedback form. I'm repeating again and again because that is also important for us. So anybody else would like to ask a question or say something?
Sir, can you suggest some reference books? I mean, if someone is want to study this from beginning.
Yeah, hang on. I'll just paste in some things for that.
I think one of his books is already there, Calculus and Financial.
Yeah, I wrote a book out of, a St. Stephen's program. But so I'll tell you about that. But there are many nice books at the undergraduate or master's level. So maybe I can just, hang on. I'll just tell you about a few books. Okay. All right, so the books I've pasted here, I think generally they could all be read at the undergraduate level, but they're of different types. So on the top left, there is Leuenberger's Investment Science. This is really written more. See, basically you have books with different combinations of how much of real world finance they get into, how much mathematical modeling they get into. Some hide the maths, some hide the finance. Okay, some are all theory without any sort of, it's not clear whether that theory works in practice. Others are all about the practice. Some are a mix. So there are different things available depending on what you want to look at. Investment science is a nice sort of conceptual introduction to what are the issues in finance with a reasonable amount of mathematics used, not too much. Some of the things done in it could be nicer if just a little bit more maths was used. But on the other hand, the idea of developing, some financial intuition, that is handled very well in this investment science book by Leuenberger. The next option, future and other derivatives, about a more advanced part of finance called financial derivatives. But this is the Bible for that. And this will tell you a lot about the specifics of how stock exchanges work, but as well as doing the mathematical modeling for many things. But the maths will generally be sort of skimmed. The results are provided. It's more like an engineering maths approach. Then this Kapinski book, Mathematics for Finance, this is more from the theory side, and it's a nice book from the theory side. But again, it's not like measure theory. It's like still calculus and basic probability. And similarly, Sheldon Ross's book on mathematical finance. Sheldon Ross's book is more about a few special topics, and Kapinski's book is more of an overall look. Okay, and then I wrote this book out of a Stephen's program, Calculus of Finance. Here I've tried to deal a little bit more with how you actually would work with data. So you're developing some theory, but how do you also keep applying with data and what issues come up with that? So there's also more of that. Next book is Statistics and Finance. So that's a bit more advanced, but again, the other books before this, you just need to know probability essentially. In this one, it's a little more of statistics. And then the last two are a bit more advanced and are maybe more suitable for master students. You need to know your real analysis, maybe a bit of measure theory to start making good sense of those. Okay. But I think these are kind of good standard books that people could start by looking at and get started on this subject.
Thank you, sir.
Anybody else has a question to ask? I think you have given enough food for thought from the beginning of investments of science to stochastic calculus. I think depending upon your stamina and your need, you can go through this and make your choice. But if you want to be a professional financial planner or something, and what is the hot sort of topic for students, you need to know stochastic calculus. So with that, let me
need to know your measure theory.
Yeah, once you decide about knowing stochastic calculus, you will have to know probability and measure theory, and everything follows as a corollary to that. So let me thank Amber for bringing the world of finance to a level which all of us could understand and appreciate. And as Srinivas said, probably gives a spark to learn and teach more about such things. Thank you, Amber. And
okay, thanks so much. It was really enjoyable being with all of you.
Hope to rope in again sometime later.
Yeah.
And
sure.
thank you everybody for joining.
Thank you, Amber. Thank you, Amber. Thank you, Rana.
Thank you. And,
thank you, sir.
Thank you, everybody, for joining. Here is a statistical result. I wanted to. You want people to switch on the video to have a picture, Soumya?
Sure.
Yeah, that's great. Yeah, let's have it.
If you all can switch on your video, probably we can have a photograph. Click the screenshot. But what I was going to say, I forgot. Anyway, I wanted to say something before.
You mentioned statistics of something. I mean,
yeah. It's really interesting that I'm getting a statistics of how many people register for an online lecture which is free and how many actually join. So 168 had registered for this particular talk. And the number went to 25 or 26 maximum who came online. So it's, I think, going again and again that about only join. So that is the hypothesis I want to test sometime probably. So testing hypothesis statistics will probably come into handy. I should also know statistics now. Okay.
Yeah, please everyone quickly open your videos if you want to have a good photo with us.
Please switch on your video so that we can take a shot. Audio, Sanjay, if you are still there, please. Otherwise, Soumya is going to say 1, 2, 3.
Yeah, 1, 2, 3. Thank you.
Thank you, everybody.
Bye.
And do join the next session.
Thank you. Yeah. Bye.
Thank you once again.